All right, I think we're recording. Okay, so welcome to the video, the first of probably a three-part on the fundamental theorem of calculus. Uh, this is a heck of a throwback to a year ago because I haven't recorded a video like this in quite some time, but I also never really apparently figured out my lighting situation. Anyways, so let's talk about the fundamental theorem of calculus. It's a bit tricky. It's a two-part theorem. On the face of it, the parts don't necessarily look like they have anything to do with each other. But I'm going to convince you in these videos that they are two sides of the same coin, and indeed you can use one of them to prove the other, which is the order that we introduce them, same as the order in the book. So the fundamental theorem of calculus part 2 is what most of us will use all the time. Fundamental theorem of calculus part 1, however, again, is sort of completing the picture, and it really is a beautiful picture. So before we state the theorem, especially part 1, because again, it is a bit tricky for students, let's understand the concepts, the sort of entities that the theorem is going to be talking about. So imagine that we have the graph of a function. We deal with these things all the time now. And let's call this starting point sum A. We think of this function as being defined and indeed differentiable and in fact, integrable, but actually in this case, continuous. So I actually want this function to be continuous over some interval. And the idea is you're used to thinking so far in this class, you're used to taking this function and going out to some point, B, and looking at the area, or maybe we should perhaps more accurately say the net area or signed area under this graph, which of course would be this area, whatever it may be, counted positively. This area also counted positively. And of course, this area counted negatively. Again, you have to be careful. Area, as many of you noted on the FA, generally means positive. We really want to mean signed area or net area here. But I actually want to do something a little bit different for a minute. I want to, instead of stopping at B, I want to stop at some point X. And I want to look at the net area under the curve between A and X. Now that's a number because the definite integral is always a number, but I'm going to turn this into a function. So g of x is the integral from A to X of my f here. So this is f, and I'm going to think of this as f of t, because we're going to think of this as the t-axis for a moment, where x then defines our stopping point. So this book, as far as I recall, does not use this terminology, but some calculus textbooks call this the area so far function. And I actually think that's a fantastic name for it. Maybe, again, we'll be clear, we'll put net area so far. The point is that what this function is doing is it's saying, you give me a number, because remember, that's what x is. It's a variable, but it's standing in place for a number. You give me a number. I'm going to put that as the upper limit of integration in my definite integral. This is a number, but of course it's a number that will now depend on x. And that's basically what we call a function, right? A function is nothing other than some sort of rule. This is not the math definition, but this is sort of the math definition for us. It's a rule that takes an input and gives an output. And so what's going on here is that we're saying, look, we're always starting here. So if I stop here, I want to look at this area, and this area. I want to count the things above the x-axis positively. I want to subtract the things below the x-axis, and that's going to give me the net area so far. So we call this g of x the area so far function. Again, if you want to call it the net area so far function, you're being a little more correct. And so a natural question then, I say natural, it's a natural question, is how does this g of x behave? In particular, is it well behaved? Is it continuous? And critically, is it differentiable? And so the answer is yes. So to both questions, because of course, if the function is differentiable, then it's automatically continuous. But in fact, the answer is that not only is g differentiable, but in fact, we already know what its derivative is. So here is the theorem. And this goes by the name FTC1. So this is part 1 of the fundamental theorem of calculus. And by the way, if you haven't encountered the word before, because this might actually be the first named theorem we've encountered, the word theorem in math simply means like a capstone result. Like generally, it is not uncommon for math papers to have like one big theorem. Theorems are the sort of the major culmination of the arguments. They're the big lines of reasoning that we use, or the big points of reasoning that we use in mathematics. So what is the fundamental theorem? And by the way, nothing gets to be called the fundamental theorem of anything unless it is literally that important. So every subject basically has a fundamental theorem, and it is basically the defining theorem of that subject. So let's see, what is the defining first half of the defining theorem of this subject? So the FTC one says g of x is differentiable and indeed its derivative is f of x. We need f to be continuous for this. I guess I should have said that probably if I were stating the theorem a little better. So continuous. If I were stating the theorem a little bit better, what I would say is let f be. I'll put it. All right, hold on. My better angels are getting to me. I don't want to rewrite all that though. So hold on. I'm gonna cheat. I love the iPad. And move it down here, and I'm gonna say, here we go. If f of x is differentiable, sorry, continuous. If f of x is a continuous function on some interval, then for all x in the interval, I'm going to use open intervals just to be safe. Could consult the book, but open intervals should be fine. So if f of x is continuous on this interval a to b, then for any stopping point, basically, that's how you should think of the x. For any x in the interval from a to b, g of x is differentiable. This area, this net area so far function is differentiable, and indeed the derivative is precisely f of x. So on some of the handouts or the Jamboards, depending on what section you're in, you might actually work through this for some very concrete, simple cases. I think it's super enlightening. As I said, I will pivot over to another video after this one where I actually give a sketch proof of this, because I think it's a beautiful sketch proof and it uses a bunch of the properties of integrals. So again, I would strongly encourage you, you're never going to be asked to sort of produce the proof in this class, but I really think it's a valuable proof to go through. And I'll go ahead and then, as I said, use it to prove the second fundamental theorem of calculus, which I'll state in just a second, but I want to call a little bit of attention here. So what is this theorem saying, right? So this theorem, if you think about it, is sort of telling us what happens if we start with a function, f of t or f of x. By the way, literally no difference between f of t and f of x. The function is really f. It's the rule that assigns an input to an output, or sorry, an output to an input. It doesn't matter whether we call it t or x. I know it can get a little confusing, and indeed it does trip students up that I've changed the name of the variable, but I promise this is not important. Because the function is just f, right? It doesn't matter whether I'm looking at y equals x squared or y equals t squared. You would think of the same parabola in either case. It's just a question of what you're calling that independent variable. There is a good reason. So I said it doesn't matter. I should be careful. There's a very good reason why this and this should have different letters. But the fact that I called it f of x here and I called it f of t here makes absolutely no difference. It's still the same rule for given a number, how you're going to produce an output. And all I care about is that rule. So it doesn't matter for the purposes of talking about f, whether we think of it as a function of x or a function of t. Again, think x squared versus t squared. It's the same function. It's just a question of what we're calling that independent variable. For the purposes of this, this area so far function, it would be very confusing to use the same variable in both cases. So that's why we don't do that. So I've switched to t. You, of course, all know this variable is the dummy variable of integration. It literally does not matter what we call it, but this one does matter. It needs to match this. So what this is saying is basically what happens if I take a function, I integrate it in some sense, and then I differentiate it. And the claim is that we get back to what we started with. So let's look at that. So you start with some function f, you integrate it. Now there are a couple ways you might do that. So you might say, well, wouldn't the obvious thing be to put a to b of f of t dt and then differentiate that? And you could try that. If you stop the video for a second and ask yourself, if you did this, if you took this expression and you differentiate it, what would you get with respect to any variable? It doesn't matter. There's, literally any variable you want, because this expression is a number. This is just a number. So if you tried that, it'd get 0. There's nothing interesting going on there. If we want something meaningful and interesting, we need a function out of this. So the claim is that instead what we do, rather than putting this upper bound of just the end of the interval, we call it x. We allow it to vary, and we ask, how does this number that represents the net area vary as x varies? So as you move x along, you can see, and in fact, if we look for a moment, if you stopped x here, then the net area, if this were little x, would be this region minus this region. As I moved x over a little bit, I would get a smaller value because I would be having more area contribute negatively. Meanwhile, the same area was contributing positively. So you could ask yourself, at what point, if you thought about it, it's a little tricky, but if you thought about it, at what point would that net area so far function stop decreasing and start increasing? Well, the minute you crossed right here, then the contributions to a little bit more are now positive. So they were contributing negative. So your function was getting smaller and smaller and smaller. Now you hit, again, not f is drawn, this area so far function here off to the side. Now you hit here, and now all the area under the curve is contributing positively, or the net area under the curve is contributing positively. So the graph of G starts to go back up. And that means that G had a minimum right there, which is actually makes perfect sense because this function, this theorem tells us that G prime is f. And remember, where a function has a minimum is where the derivative goes from negative to positive. But if the derivative of G is f, it precisely went from negative to positive right at that spot. Like, again, you're going to work on this on a handout or a Jamboard, but it makes so much sense when you really understand what it is that this function is measuring, what the net area under the curve is capturing. Like, you can ask yourself, until what point, so you start with an x here. So far the function value of G is kind of small because I just get this thin, sort of trapezoidal looking piece. As I move x over, I'm still increasing because we're just accumulating more and more positive area. It's above the x-axis, but that accumulation that will stop right here. Once x flips from positive to negative, we now start accumulating negative net area. So that's going to start subtracting. So again, G is going to have a maximum right at that point. It will have increased up until the function f cross zero, and then start decreasing. And again, what is a maximum? The derivative goes from positive to negative, precisely what we see here. It really makes a ton of sense, and this theorem just codifies that relationship. So again, instead of putting a number here, b, which would give us a single number and therefore no interesting derivative, we put x. We allow the upper limit of integration to be this function, this variable, and we basically ask, how does that area change as x changes? And then that now becomes a function, and when you differentiate it, what you get back is f. In other words, the two processes are basically undoing each other. They're inverse processes in some reasonable sense. Okay, so again, I'm in a separate video, I'll give a proof of this, but in the hopes of not making this video too long, although it's always long because I always talk a lot, let's see what the flip side of the coin says. So the flip side of the coin talks about, well, basically, if this told us how to start with a function and sort of integrate it and then differentiate it, you might ask, what happens if we try doing things the other way? What if we started with a function, differentiated it, and then tried integrating it? And that's exactly what the fundamental theorem of calculus part 2 basically says. So in the usual manner of using a capital F to denote an antiderivative and the lowercase f to denote the derivative, so we can ask, what if you were to differentiate? So you get a little f, and then what if you wanted to somehow integrate that little f? And the question is, would you get back something that had to do with capital F? Now, technically, you lose information when you differentiate. So this is a little bit tricky, right? That's why antiderivatives always have that plus c. Because I could start with a function, I mean, just to be clear, I could start with a function x squared, or I could start with a function x squared plus 7. They have, in both cases, the same derivative of 2x. So when I integrate back, I don't know which of them I started with, and this is why we get this x squared plus c term. In fact, that is all you get, so that's sort of amazing. It's a consequence of something called the mean value theorem, that in fact, the only difference that you can end up with, of course, is that the plus c. So everything else is defined, but you get this plus c. We refer to this as the constant of integration. I'm sure most of you know this. If you don't, you will see it anytime we take an antiderivative. but that isn't a definite integral, because definite integrals are number. Anytime we take an antiderivative, we're going to get this plus c around. But basically, what this says is, what the fundamental theorem of calculus says is that what you get back is effectively what you started with respect to this plus c, and it captures that idea a little bit differently. So what it does is it uses this idea to tell you how to evaluate definite integrals. And this is a hugely, hugely powerful method, because at the moment, as I'm sure you are aware, and you'll see in the FA, the only way we have to evaluate definite integrals is from the definition. And if you think back to something like the limit definition of the derivative, you never want to evaluate something from the definition. The definition is beautiful. It's a beautiful theoretical tool. It explains what's going on, and it's generally horrible for computation. So what does the FTC part 2 tell us? And it tells us how to, so it sometimes literally goes by the name, the evaluation theorem. And you'll understand why in a second. But again, I promise once I state it, I'll show you that it is just filling in. And this is particularly true if you go look at the proof, which, as I said, I'll do in that optional video. It just fills in this other side of the coin. It basically talks about what if you started by differentiating and then integrating, what happens? So just to be clear, let me put question marks here because it's a little more complicated than what I just wrote, but what we're going to write down is a very specific form. So what does the FTC 2 say? It says if f of x is an antiderivative of little f of x, i.e. capital F prime of x is little f of x, then any definite integral involving little f is very easy to solve. So if I have a definite integral involving little f, notice this is a number, right? Everything, this quantity here is a number. So I need some number. And the answer is, it's the capital F, my antiderivative that we started with, evaluated at b, the upper limit of integration, minus capital F evaluated at a, the lower limit of integration. And for what it's worth, notationally, we sometimes write this, or we'll often write this as capital F of x, vertical bar to denote evaluating, b, the upper limit of integration at the top, a, the lower limit of integration at the bottom. Again, this is just shorthand notation for this expression. I'm going to go through the proof, but I want to not belabor that, but I just want to say a couple things real quick. So what this is basically saying, so you could rewrite this for what it's worth. Should stop the video for a minute and think about why what I'm about to write is true, but what this is saying, so remember, we assumed that little f was the derivative of capital F, because we assumed that capital F was an antiderivative of little f. So there is no harm in replacing this occurrence of little f by this occurrence of big F prime. And so when you see this, what this is saying is, this is what happens if you start by taking the derivative and then integrating that derivative. Now, again, because we're phrasing it, and we don't have to phrase it this way, but this is how it's generally phrased, because we're phrasing it as a definite integral, what we needed at the end was not a function like what we got before, but an actual number. The claim is it's this number. And you might say, how does that work? There are lots of antiderivatives. Why do they all give the same answer? If you did ask that question, then fantastic on coming up with a wonderful observation so quickly. If you didn't, and I stole your thunder, I apologize. But real quick, let's see how this works in actual practice. So let's suppose that I want to do an integral, which would take you a little while. It's not impossible, and we certainly have the tools to do it. But let's say I wanted to do an integral without using the definition. So you could do this from the definition. You might see something that looks similar to this on your Friday assessment. I want to show you how much quicker it is. I would actually invite you to pause the video for a minute and try doing this from the definition. Again, it's 100% doable, but it takes a little time. So I'm going to show you how ridiculously quickly and how powerful this evaluation theorem is. So we look at this and we look at our integrand. So our integrand is x squared. We have to find an antiderivative of x squared. You might be worried that it matters what antiderivative we pick. I'm going to show you in a second that it won't. But just to be clear, let's pick two. So let's find two antiderivatives of x squared, and we'll see that the answer works out the same for both of them. So you know from F2, you are familiar with basic antiderivatives, and you know that x squared is going to come from something that like 1/3 x cubed, but you also know that you could have chosen, say, 1/3 x cubed plus 4. Check for yourself for a minute, take the derivative of both of those, you get x squared in both cases. So this is what we're going to call our capital F of x, and I'm also going to call this capital F of x. Again, it's a little bit of an abusive notation, but we're going to see that it works in both cases. So the fundamental theorem of calculus part 2, the evaluation theorem, tells me that since this f of x here in either case is an antiderivative of the integrand x squared, excuse me, that we can evaluate this integral by writing it as, so 1 to 2 x squared dx is 1/3 x cubed from 1 to 2. So here I've used that vertical bar notation that was introduced above. So I took my antiderivative, I wrote it here, I put the bar to represent evaluation. This 2 was my original upper limit of integration. This 1 was my original lower limit of integration. And from the notation, we know that means 1/3 2 cubed minus 1/3 1 cubed, which is 8/3 minus 1/3 or 7/3. So that's my answer. Now, again, you should, if you're not, say, wait a minute, but there were lots of antiderivatives, so why didn't it matter? Fantastic question. Let's see why it doesn't matter. So on the other hand, we could have tried it the other way here, and we would have written this as 1/3 x cubed plus 4, big bar from 1 to 2. So here, again, same idea. We're using the vertical bar notation. We're using a different antiderivative. And what we would get is 1/3 2 cubed plus 4 minus 1/3 1 cubed plus 4. And you might just already see what's happening. So critically, we pick the same antiderivative to evaluate at the top and the bottom. That means whatever constant we choose, and again, any constant is fine, 4, pi, 17/3, e squared, it doesn't matter, right? But the key is whatever occurs here is also going to occur here. They're being subtracted. So they're just going to cancel. And indeed, we see that this simplifies to exactly the same expression up above. In particular, we still get 7/3 as our answer. So again, there's a way, and it comes out in the proof of the second fundamental theorem of calculus using the first. There actually is a way to phrase this that looks a little bit more like the exact counterpart of the first. It's just not the way the book phrases it, so I'm not going to mention it here. Again, if you watch that proof video, it will come out. But you can understand now. So first off, that was way better than solving it from the definition, right? The definition of the definite integral is a wonderful thing. It has all sorts of wonderful geometric intuition. It gives a clear indication of what's going on. We're approximating areas by rectangles. We're taking a limit so that the error goes to 0, but it's a cumbersome process. This was much easier. And as a result of this theorem, what this tells us is that solving any integral in this class reduces to finding antiderivatives, right? When we have a complicated integral, we now need to find an antiderivative. So, if you wanted to use this same trick on, say, an integral that looked like this, 0 to pi of, I don't know, 1/3 cosine of 2x dx, again, I don't want to put that into the definition. You definitely don't want to put that into the definition. We haven't equipped you with enough understanding of how to handle those sums to even compute this from the definition. So for things like this, we're going to use the fundamental theorem of calculus, but what it means is we need to find an antiderivative. That's probably not that obvious to you, although with a little bit of thought, you might be able to get it. So the main bulk of the middle portion of the class is just going to be spent learning tricks and tools, not tricks, but tools, methods on how to find antiderivatives of complicated functions. This is U substitution, integration by parts, partial fractions. We don't necessarily cover it in this class, but trig substitution would be another example. There are lots of these tricks and all they're doing is enabling you to find antiderivatives of increasingly complicated functions, because if you can find an antiderivative, then you can solve the problem. You can solve the integral without really doing much work at all, just the work involved in finding the antiderivative. I'll cut the video here, but I'm going to hop over. And again, I would invite you to come watch, because I think it really is a beautiful proof. And I'm going to quickly prove the two functions, not prove, mostly prove. It's a heuristic idea that with some work can be turned into an actual proof, certainly good enough for this class. If after you take Math 23B, which we certainly hope you all will, you want to come back and actually turn it into a proof, that's fantastic. You would also do this in Math 110A, the real analysis course, which is a great class. But I'll cut the video for now. Again, if you're not interested in the proof, that's okay, but definitely worth checking out. Yeah, anyways. I don't actually remember I don't remember how to cut the, it's been too long since I used it. Here we go, got it.